Okay, students, welcome to video class number 12. And the heading that I give to this session is time domain analysis of first order system. Now, before going into this first order system, I would like to continue on the topic which we started in video class 11. That is, some more basics are there. That is, in the last video we stopped with the transfer function of a closed loop system, and we have seen or explained what is zeros and poles, and what do you mean by characteristic equation. So again I repeat, transfer function is nothing but it is of the form P of s to Q of s, and for a general closed loop control system, that will be gs by 1 plus gshs. Okay, now we have seen in the last video, when you equate p of s to 0, you will get a both are polynomial of s, so it can be of different orders. So when you equate this p of s to 0, you will get what is called as the roots. When you solve this, you will get the roots, and the roots are called as the zeros, while when you equate q of s to 0, you will get the poles of the system. Say for example, if it is say s square plus 2s plus 1 divided by s cube plus 3s square plus s plus 1, meaning this is a polynomial, right? And this one is another polynomial, this one is another polynomial. So this can represent, this is your p of s, this is your q of s. You can individually equate these polynomial to 0 to solve the roots, and you will call these roots as zeros and poles. Now, as in this equation, that is for your, and what is the specialty of this function? This is actually your transfer function of a general closed loop system, any closed loop system. So you can also equate the denominator to 0. That is, when you equate, so this 1 plus gs is again a polynomial, right? This is a function of s. So 1 plus that function of s is going to be again a function of s. When that is equated, you will get an equation which we called as the characteristic equation. And it is called as a characteristic equation because this can give you more information regarding the various characteristics of the system. So this is 1 plus gs is equal to 0. When you solve this, what you are going to get is, this is actually the q of s of this transfer function. When you equate this, you will get what is called as a poles, and generally we have seen that these poles and zeros are called as critical frequencies, because why they are called as critical means that will drive the transfer function either to 0 or to infinity. Okay, now let's move on to the next topic associated with this. So after that, we'll be dealing with the first order system. Okay, the influence of a closed loop pulse on the transient response. So what do you mean by closed loop pulse? When you equate the characteristic equation to 0, these poles are called as the closed loop poles, meaning they are the poles of a closed loop system. That's all. Closed loop poles. Now, this particular pole has got some effect on the transient response. So, by the way, we have also seen what do you mean by a transient response in the previous video. So, we'll again start with the basic transfer. Okay, now we'll start with this transfer function, which is given by z of s by r of s is equal to g of s by 1 plus gshs. And from this you'll be able to get c of s is equal to r of s into g of s by 1 plus or minus g of s. Now this is again a function of s. Now if you can find out the inverse, that is c of t, small c of t, right? So c of t, you'll be getting a function of time, right, by finding out the inverse of c of s. Now you can plot this. So this is actually a time domain or response, or this we call as a time domain response of the system. So once you get the c of s, if you take the inverse, you will get the C of t, or it is called as a time response. Now, using the C of t, this is called as the output response as well. Now, using the C of t, you can make a plot versus C of t versus t. So you'll get a graph, something say like this. So you will be getting a graph. So imagine just an arbitrary graph I have shown. So this gives you a response, how the system behaves to each input. What is RFS? RFS is actually the input. So do remember, in your control system, the input is RFS, the output is C of S. So the corresponding to that input, so this C of t actually depends on the, not only depends on the transfer function, it also depends on the input. Now based on the input you will have a different responses. Now say initially, so from at t is equal to 0, that is at the application of the input, it starts to respond, right, at t is equal to 0, but it won't be coming at the desired value. That's what we were talking about throughout these sessions, right? So that the study, that is the transition of the system from t is equal to 0 to a steady state is what is called as a transient response. Now, this transient response will be having or will be having the effect of closed loop poles, or closed loop poles will be having an effect on this transient response, and that's what we are going to study under this heading. Okay, so let's start with different cases. Okay, so case one is a simple pole at the origin. So I'll just give you an example, the meaning of a simple pole. The simple pole is, say for example, just consider an example, s by s plus 1 into s plus 2, a function. So we know that what is a pulse? So pulse is equating this to 0. So when you equate this to 0, you will have two roots, that is, it can be s is equal to minus 1 or it can be s is equal to minus 2. And we know how to plot the pulse 0 plot. Now the zeros, so these are called as p1, p1, and this is p2, right? And you have a 0 at z is equal to 0, that is when s is equal to 0. So you will be plotting like this, right? So you will represent s is equal to 0, that is by a circle, so this represents a 0, and you will have a pole at this minus 1, and that will be marked by an into sign, that is, this is minus 1, this is minus 2, and this is 0, right? So we'll say that all these poles and zeros are called as simple poles because at a particular location you have only one single Paul. Say, there can be a situation, say something like this. Instead of this, if you assume this s by s plus 1 the whole square, right? If you take the poles, here also you have two poles. But the poles will be, again, always at s is equal to 1, and p2 is also equal to s is equal to 1. Why? S is equal to minus 1. Why? Because you are actually representing s plus 1. This is actually what? S plus 1 into s plus 1. Equating each to 0, you will be getting two poles sharing the same location, right? S is equal to minus 1 is a location. So there you have two poles corresponding to s plus 1 and s plus 1. So this gives you an idea that this at this particular location you will represent, you have two poles, or you will call those poles as the multiple poles. And here in this case you will say this is a multiple poles with the multiplicity, let us call that as k is equal to 2. The repetition of the poles at a particular location is what is called as a multiplicity. So from this you understood there are two different types of pole, or as well as zeros. So this is applicable to zeros as well. So a simple pole is a pole which has got only, which I mean in a particular location it will be having only a single pole, while multiple poles are in the same location will be having more than one poles. So as in this example, so those are called as multiple poles. Now let's come back to this case 1. Say it is the case where you have a simple pole at the origin. Say I'm going to write an equation, say c of s sometimes you may be getting, say, something like this, k by s. Okay, so after putting your r of s and substituting this g of s, imagine that you got your c of s to be k of s. Now how will you draw the s Paul zero plot of this? When you plot this Paul zero plot, you can see that you have at s is equal to 0, you have a Paul. Now we are going to study the response, the effect of this. What is this called? This is actually a simple Paul. Why? Because at z, a simple Paul at the origin. Why at the origin? Because this stays at the origin at s is equal to 0, right? Now, not only that, why it is called as a simple Paul? Because at that location you have only one Paul. Had it been a square, you will say that you will have two Pauls with the multiplicity 2, right? So this is k by as. And when you take your c of t, what is the meaning of c of t? Taking the inverse. So we are actually interested in the transient response, the effect of this closed loop Paul, this open loop Paul, this simple Paul on c of t. So we need to find out the inverse. No, we know that this k is a constant, while k by es, right? So what will be the c of t, or the inverse of this? So when you take the inverse, okay, mind you that this k and this k has no relation. Okay, this is multiplicity, and this is simply a constant, k by es, or this you will get this as k into what is the Laplace inverse of 1 by s, which is k into u of t. Now if you are to, so this is actually your s domain, that is sigma plus j omega. Now you can throw this is actually your time response, that is c of t. This is actually plotting the Paul zero plot in an s plane, while you can plot the same thing in a time domain graph. So that is c of t is actually equal to k into u of t, meaning you will represent that as a constant. It remains a constant, right? So this is the impact of a simple Paul at the origin, right? The response remains. So what you conclude is, the conclusion is, the response remains a constant, right? Constant for all values of t, when you have when you have only simple Paul at the origin. Do remember, it is only when you have the simple Paul. Now when you have different combinations of Pauls, then the response can change. So this is the case where you have only one Paul for the system, and that is located at the origin. That's the case. So in that case, what you're going to infer is, the conclusion that you can draw is, from the time responses, the response remains a constant for the whole value of t. Okay. Okay. Now, next case is a simple Paul on the negative real axis of S plane. Say, I'll just give you an example of a C of S. So you got a C of S to be, say, some k divided by S plus 3, right? Now if you have such an example, now when you equate the denominators to 0, you will get the Paul to be S is equal to minus 3, and if you are to plot in an S plane, you will be getting this as, so you'll be getting a simple Paul at minus 3. Why simple Paul? At this location you have only one Paul, and that too in the left half of the S plane. That's why it is called as a negative real axis. This is a real axis, and that to the negative portion of the real axis. So this is the negative real axis simple Paul case. Now let us see what is going to be the impact of this simple Paul which is residing on the negative real axis. Say for example, and now we are going to generalize, say k by s plus, say, some sigma 1, right? Now we know that when you take the inverse of this, okay, that is when you take c of t, it is a Laplace inverse of k by s plus sigma 1, and we know that this is, say, k into e raised to minus sigma 1 into t, right? Where sigma 1 is a positive quantity. Sigma 1 is a positive quantity, right? So this is it. So what is s plus sigma 1? When you equate this s plus sigma 1 to 0, you will get this as minus sigma 1. So that means you can plot somewhere here. So this will come at the minus sigma 1 means s is of the form sigma plus j omega. There is no j omega, meaning this point lies on the real axis, and that too in the negative half. Now let us see the impact from the time response. When you just draw the c of t, that is, when you draw the c of t or the time response, what happens at t is equal to 0? When you plot, say at t is equal to 0, this the value of c of t at t is equal to 0. Put t is equal to 0 here. So you will get this as 1. C of t becomes constant k. So okay, this response starts from a constant k. Now what happens at c of t at t is equal to infinity? At t is equal to infinity. So when e raised to minus infinity, that is 1 by e raised to infinity, or this becomes equal to 0. So we understood that as t increases, what happens? The response decreases, and finally it arrives at a point 0. So this is, no, you cannot touch it. It will be touching the real axis only at t is equal to infinity. So that means this is an exponentially decaying signal, right? So the impact of this is the response decays from 0 to t as t approaches infinity. So this response decays, right? Decays to 0, right? So now what happens when it goes farther and farther? So as your c of t, so the sigma 1 goes farther means on to the, again, to the farthest of the left side of the s plane. What happens is the decaying response is going to be faster, because, right, say for example, say this is it. Say sometimes, when you draw the c of t for a particular sigma 1, this will be like this. Now if this sigma 1 is, say, consider sigma 2, where sigma 2 is much less than sigma 1, that means in the negative half it is going away from that, say, as in this case. Okay, so this is sigma 1, and what is sigma 2? Sigma 2 is somewhere over here. So you can see that the response is going to be like this. That means this is a faster response than this. So this decaying to 0, the output, and so what we are going to conclude is the decays to 0 means the output will not be having a variation. So in the case 1, we said that the output remains constant. So as far as a control system is concerned, the output will not be varying. It remains, I mean, so the control, the response remains a constant, while in the second case we've seen that the response decays to 0, and you can make it faster as the pulse goes farther and farther in the negative half of the s plane, right? So we can say that as it decreases to 0, from a stability point of view, you can say that the system is going to be a stable system, right? So the changes in the output will not remain a constant, um, or it is not increasing, or any changes in the output will be decaying to 0 in the case of a simple pole on the negative real axis of the S plane, right? Now let's move on to case 3. Okay, now the next case is a simple pole on the positive real axis. Okay, so that is just opposite to the case which we studied in under case 2. So an example, just for your information, an example is k by s minus 3. Now when you equate this s minus 3 to 0, we will get s is equal to 3, meaning when you draw it in the s plane, the pole you will be locating at the positive real axis. So this is of the form sigma plus j omega. You know that omega is 0, only you have sigma part. That means this is on the real axis. Now we are going to find out the impact of this Say consider SC of S given by K by S minus sigma 1. Now, we know that when it becomes when you find out the inverse, your C of t becomes K into e raised to sigma 1 into t. So what happens is, okay, when you draw C of t, you can see that at t is equal to 0, at t is equal to 0, what happens? Your C of t becomes k, right? So it will start from k, but instead of decreasing, what you can see is at t is equal to infinity, this is also a positive quantity, so there is no negative exponentially increasing function. So you're going to get a graph like this, it exponentially increases. So what does this suggest? So any error at the output of a control system that grows exponentially if the pole lies on the positive real axis, while in this case if there is any error, that gradually as time progresses that reduces to zero, while in this case if there is any error that remains as such as long as the pole is at the origin. Okay, so you must think in this line, in the perspective of a control system, then you will understand. So this system, you can say that this system switches to instability, or this is going to be an unstable case. So this is an unstable case, this one is a stable system, and you can say that as it remains a constant, you can neither classify as a stable system or an unstable system, or you can call this as a case of a marginally stable system. That means it can go either to the left or to the right. That's it. Okay. And the next case is a pair of conjugate poles. So I will just explain. So before going into that, you should know what you meant by this conjugate poles and how it resides on j omega axis. So I will just give you an example. Say for example, if you have a CFS, say something like k by s square plus 2. And what you do is, in order to find the poles, you will be equating this denominator to 0. Now what is the impact of this? So s square is equal to minus 2, right? So s is equal to root of minus 2, or you can say that this is root 2 into j, right? Right? So this is equivalent to sigma plus j omega. So what do you conclude this? Here you have sigma is equal to 0, while root 2 is omega, right? Omega is equal to root 2, right? In comparison to that. So such a pole actually is on what? Is on the omega axis at a point root 2 j. So s is actually at root 2j, meaning it is at 1.414 j. Okay, now one more point is to be noted is, when you take the root, s square is equal to minus 2, as you have studied, this is not simply plus itself, this will be plus or minus. So this will be plus or minus, so this will be plus or minus. What's the meaning of that? So what is the meaning of this? This pole is not a real pole, this is a complex pole, right? Complex pole with real part equal to 0. That means that lies on the imaginary axis. And not only that, if there is a complex pole, we can see that since it is complex in nature, as you studied in your lower classes, always the complex numbers existence conjugate. So if you have some plus j, then you will be having some minus j. So you have a plus root 2j, meaning you have a minus root 2j. So it always exists as a pairs. Now you can have the plot of this. So when you plot this, you can see that this lies on this axis. This is your imaginary axis. Say call this as, say, minus 1 point, so plus 414 j. That means exactly at the negative side, negative point, this much magnitude in the negative side, you can find one more pole. This is minus 1.414 j. Mind you that this is not a multiple pole, because these are at different locations, but they are conjugates, right? Because this is one is plus 1.41 for j, another one is minus 1.41 for j. Now we are going to study the impact of this scenario on your C of t. What happens when you find your C of t? Okay. Okay, now I will explain this case by using this example itself. I'm not going for the general case. So you can represent this k as s plus root 2 I into s minus root 2 I. Okay, so you can just prove by simplifying. You can will be finding that this is s square plus 2, right? Now, this is your, this is your C of S, sorry, this is your C of S. Now, how will you find out the C of T? You know how to find out C of T, splitting this as partial fractions, say, call this as K1 by S plus root 2 I plus K2 divided by, resolving this into partial fraction, you can write like this. Okay, now this is C of S. Again, this is C of S. Draw. Now from this you can evaluate your C of t. C of t is you can find out the inverse of this. Now what will be the inverse? This will be say k1 into e raised to minus root 2 I, right? Or j, whatever you call, plus k2 into e raised to plus root 2 I, right? Okay, now, or root 2 j. Now what is actually e raised to minus, say, minus j omega? So from Euler's identity, you know that this is cos omega plus minus j sine omega. Now, if you can expand this, you can see that this will be uh, cos root 2, okay, this is cos root 2 minus, okay, root 2 minus sine root 2 I plus k2 into uh, plus k2 into cos root 2 plus j sine root 2. Okay, so imagine that this root 2 is a, here you have a constant. So if it would have been a variable, say something like omega, you will be getting some cos omega, I sine omega, cos omega, sine omega. Okay, so that means this is going to be a, so as omega varies, this also varies, right? That's the meaning. So this I've just taken as an example. Now this can be some omega, right? Now if this had it been a variable, what you see is you can see that this actually varies according to omega. That means we know that this is a sinusoidal thing, right? So the response is going to, yeah, how will it be? This will be sinusoidal nature because of the presence of this term, this oscillatory. Or you can conclude that the response actually oscillates, but, and can you find any damping here? No damping. This is a constant. This one is a constant, and constant cannot decrease the oscillation, or it cannot prevent the oscillation. So it will be constant. So it will be always providing a constant oscillation or a sustained oscillation in this case. So here also you can say that the output oscillates, but the oscillation is neither growing nor decaying. Its oscillation remains the same. Okay, we'll come to the stability aspect later after studying the other two cases. Okay, now coming to the case 5, where you have a conjugate poles on the left half of the S-plane. So uh, how will you represent that? So when you, if you want this case, say I'm just giving you an example. Let's study actually from an example. Say consider your C of S to be, say, something like this: s square plus 2s plus 2. Now you know that since when you take the b square minus 4ac, that is going to be negative. That means this is going to give you a complex pole. Okay, so when you solve this, what you're going to get is So when you equate this to 0, you will get the poles P1 and P2 as, so you may just solve and you can find it to be minus 1 plus j, the other one is minus 1 minus j. Now if you are to plot these poles on an S-plane, right, on an S-plane, what you get is minus 1 is here, right, on the left half of the S-plane. Now plus j is 1 unit up and minus j is 1 unit down. So this is minus j, this one is plus j. So you will locate this. Look, right? Now the difference between the previous one is this resides on the imaginary axis while this one is on the left side of the imaginary axis. So you can have this as k divided by s minus of s minus p1 into s minus p2, right? You can write like this. So instead of p1 you can write this as minus 1 plus j and minus 1 minus j. So you can say, you can split this as I told you. So k by, say, let it be, say, some a by s minus p1 plus b by s minus p2. So imagine that you have found out this a and b. Okay, that's immaterial right now, just for the discussion. Now what will you get for c of t? So as you know, this will be e raised to p1t, right, plus a into e raised to p1t plus b into e raised to p2t. Now substituting this e raised to p1, what is p1 here? So this is a into e raised to, now for the sake of explanation I'm just ignoring this. Okay, I just want to make you a point clear, that's all. So I'm simply substituting, so just to simplify this, I'm just simply ignoring this, just substituting this as minus 1 plus j into t, or you can write this as a into e raised to minus t into e raised to jt, right. So what is this? A into e raised to minus t into, this can be written as cos, yeah, by applying Euler's identity, this is cos t plus j sin t. And we know that this one is oscillatory in nature. So this one is oscillatory in nature. So as concluded in this case, the response oscillates. But there is a difference. Along with this oscillation, there is a term called e raised to minus t. Now what happens as t increases? So as t increases, as we have seen earlier, this exponentially decays. So when you try to plot the output graph, it will oscillate, it will start oscillating like this, but as time progresses, now, when you just mark this peak, you can see an exponentially decaying graph. Meaning, what's the meaning of this? Actually, the output oscillates, but that oscillation decays as time progresses, or you will call this process as the damping. So which term makes the damping possible? It is this exponential term. That means, again, the oscillation gets nullified. So this is the case where the complex poles resides on the left half of the S-plane. Now moving to the case 6. Okay, now coming to the reverse of this, which we have studied right now, conjugate poles on the right half. So that means what you're going to expect is a pole on this side, right? Pole on this side. So for that, I'm just say considering your C of S to be, say, k by, right, s square minus 2s plus 2. So when you take b square minus 4s, so you're going to get this as the poles to be p1 to be 1 plus j and p2 to be 1 minus j. So we know that this 1 comes over the right hand side, but this will be minus j, this will be plus j. So this point is 1 plus j and this is 1 minus j, right? So you have the poles at this location. So this is the poles on the right half of the S-plane. Now, I mean, approaching like this, you can say that, so you will be getting this as A by, right, A by S minus P1 plus B by S minus P2. Now, when you take this as, when you take the inverse of this, now just ignoring this for the sake of simplicity, you can see that this will be A into e raised to plus t into cos t, say, let it be anything, okay, a raised to cos t plus j sin t, right? So what is this? This is actually giving you an oscillation, right? This gives you an oscillation. And not only that, this e raised to t, this is going to be a problem, because as time increases, this function increases exponentially. So when you try to draw the graph of this, what are you going to find out is, when you try to find out c of t versus t, it starts with the oscillation cos t, and as the cycle increases, okay, the figure you should draw a bit more clearly. Okay, so look at this. That means, what do you see? This exponentially, so the oscillation increases exponentially, right? Or you will say that there is no damping, or the reverse of damping is taking place because of this e raised to t, right? Now, coming to, we are again to see, going to see these three cases which we studied. So in the perspective of controlling an output, here the response oscillates. That's not desirable for a system, right? But this oscillation remains a constant. Well, what about this? The, as far as the control is concerned, the, even though there happens to be happens to be a oscillation that is decreasing as time increases, right? So you can come to a conclusion that this denotes a stable system, right? This denotes a stable system. While, what about this? It is the output exponentially increasing, the oscillation increasing. So from the stability point of view, or from the control point of view, you can say that the output for the control, the output of that system keeps on increasing without any control. So this is a case of unstable system. While, as I've explained in the constant case, this is providing a sustained oscillation. So you can call this as a marginally stable system. So that means this is a point from where it can either, so this can either go to this side or to this side. That means this is so these are the influences of the poles, closed loop poles on the transient response. Okay, hope things are clear. Okay, one more point is some terminology. So what do you call this? This condition we call as, where there is no damping, we call as undamped oscillation or undamped condition, while this is called as a underdamped. Okay, underdamped or damping. Underdamped means the system is under damping. Now, this is actually, this is called as an exponentially increasing oscillation without any sort of damping. So, okay,